So we're discussing in this section the application of age distribution theory to chemical reaction systems. And age distribution, the basic concept is that things reside in a space for different periods of time. So the age in this case is defined as the time spent in the space. In our context, it's a reactor. So we've got a reactor and we've got fluid elements that are spending different periods of time in there. And so by fluid elements, I mean oil droplets or gas bubbles or solid particles. So these elements of a fluid are flowing through the space, and some fluid elements will take a route through that might see them exiting pretty quickly. Other fluid elements might take a more circuitous path and they might end up circulating in the space, and so they might take longer than they will take longer than some other paths. So there's a variety of different possibilities in getting through this reactor, and that means that different parts of the fluid will pass through it over different periods of time. And it's this difference in time that translates to a difference in the extent of reaction that we see. So let's say this reactor was maintaining a certain condition. Like let's say we were operating at a certain temperature in there, and there was a reaction happening in these particles. So say these particles were reactive. Let's say these particles came in as pure A, and then that A was converted to some other product, let's say B, and so particles that spend a short period of time in there won't be converted to a great degree, whereas others that took a longer period of time may have more B in them. So if we were to expand on an individual particle, you could think of A as being an unreacted core. So let's say this core was A, and depending on how much time that particle had spent in the reactor, you would have a different core radius. So if you had been in there for a long period of time, then the radius would be smaller. And that's what's going to determine the overall conversion of these particles through this reactor. So that's the interest in age distribution theory. We want to know what's the reaction rate in this space, given that our fluid elements are spending different periods of time in there and hence reacting to different degrees. So in what we've just said there are a couple of different concepts. One is that the routes that we take through this reactor, those we can think of as the hydrodynamics of the system. So how are things flowing through the space? That is, what's the velocity vector field behind this? The design, the geometry of this reactor, that's going to affect how fluid does flow through this. It's going to affect the circulation patterns and so on. So that's the idea of hydrodynamics. So hydrodynamics is going to affect the time spent by our fluid elements in there. And then the other thing we discussed was this reaction that's happening in the individual elements. So the kinetics behind the reaction rate, that's also going to determine the overall rate of conversion there. So we have kinetics and hydrodynamics. And what we are trying to do here is determine what the net result of these two might be. So understanding the reaction rate, if we have the reaction rate expression and so on, and if we also know how the fluid is flowing through the space, then from those two together we should be able to get to the overall reaction rate. So there exists some average reaction rate in this reactor, and we need to know what this is to design the space. We need to know how big to make this reactor, how many cubic meters do we need to ensure that we get a good reaction rate there. So we are looking in this section for some way to combine these two things. Now, kinetics is already fairly well defined, so you will by now in this course have seen enough of how you can get to a reaction rate expression and so on, so we assume that's well taken care of. and we're going to focus now on hydrodynamics. So how does the fluid flow through the space? How does this connect with our understanding of perfect mixing and plug flow and these other types of hydrodynamics that we've encountered so far in the course? So hydrodynamics is our emphasis, and we are going to, in a sense, characterize hydrodynamics in terms of age. So we know this is about age distribution theory. It links to how much time we've spent in there, and so we are going to try to estimate the age distribution, the proportions of fluid elements that have been there for different periods of time. We want to relate that to the hydrodynamics of the system.